In this video, we will be talking about one of the convenient applications of integration, which is finding the area between two different curves. Up until now, we've just been looking at the area between the x-axis and a particular function, but now we'll take two different functions simultaneously. This first graph is talking about something, or this first slide is talking about something that might seem sort of obvious to us, looking at even versus odd functions. As a reminder, an even function is one that is symmetric about the y-axis. So it's got an equal amount of area on the right-hand side of the y-axis and also on the left-hand side. And all this is saying is that rather than taking the integral from negative a to a, we could look at it from 0 to a and we could just double it up because the two areas on either side are the same. So that seems sort of obvious, right? And then the other one, an odd function is symmetric about the origin. A way to think about that two ways. One is that if I took the function and I reflected it over x and then reflected it over y, I would get the same thing. Or another way is to think about putting your finger on the center of the origin and spinning it around 180 degrees, and the function would look the same. So for an odd function, if I integrate between negative a and a, the overall area is going to be 0 because the blue areas are canceling each other out, one being negative and one being positive, and then similar for the orange areas. These are very specific to even and odd functions. We're going to look at different sets of functions where we've got two curves. In this case, maybe we're looking at some curve f of x like this here, and then also g of x between two particular boundaries. We're looking between a and b, and if I wanted to find the area of that whole blue region there that looks kind of like a fish, the picture below it is saying, well, if we think back to what we were talking about in terms of Riemann sums, we could break it up into smaller rectangles, sum them all together. But let's look at any one in particular rectangle, the one that's highlighted as being pink there. This picture up here is saying, well, if I wanted to know the area of that individual rectangle, the height of it would be, let's see, f of x is this distance, g of x is this distance, but we know that g of x is a negative number. So if we want to add those two together, if we want to take f of x and then add on the absolute value of g of x, knowing that g of x is a negative number, we're going to take the opposite of it. So that's where this negative sign is coming in. That negative sign is coming in because we know that's below the x-axis and we want to get the absolute value. Well, what were to happen if both of the curves were above the x-axis? Could we use that same formula? Let's say that we had a function like this, f, and let's say we had another function like this, g, and we wanted to find the area between those two curves. What would one in particular rectangle, what would the height of that rectangle be? This value is f of x. This value is g of x. My argument is that f of x is this distance, g of x is this distance. Oh, my pen stopped working here. So this distance here is still the same thing. It's still f of x minus g of x. So that's the height of our rectangles. Again, d of x is the width of our rectangles. So we're just saying that we can use the same ideas of taking integrals, which came from Riemann sums, and take the upper curve, take its integral, and subtract off the lower curve to get the area between them. Let's look at two examples. In this example, we want to find the area between a curve above, 2 times e to the negative x plus x, and the lower curve, 1/2 e to the x, and bounded between the y-axis, where x equals 0, and then the line x equals 1. So what we're going to do is we're going to take the integral from 0 to 1 of the upper curve minus the lower curve So 2e to the negative x plus x, subtracting off 1/2 e to the x, and then dx. Okay. Let's look at this right here. We have the integral of 2e to the negative x. Well, the 2 can come out into the front, right? The 2 doesn't really matter in what we're doing. Let's do a substitution and see what happens. Let's let u equal negative x, the exponent that we have up there. Then du is going to be negative dx. So I think I need to add a negative sign in here and put a negative sign on the outside to balance it out, so that this will end up being du. I'll have e to the u, and I've got this -2 along for the ride. That's something that's easy for us to evaluate because we know that the integral of e to the x is just e to the x. So I think this is going to be -2 e to the u. So, and then making the substitution back, this is -2 e to the negative x, going back to our original substitution. That was a lot of work for me to calculate that first term here, the integral of that first term. I think it's going to be -2 e to the negative x. The second term will bring the power up by 1 and divide by the new power. And then for the third term, the 1/2 is along for the ride. The integral of e to the x is e to the x, and I'm evaluating between 0 and 1. All right, plugging all of this in, I have -2 e to the -1 plus 1/2. I'm plugging 1 in first. And then I'll subtract off, plugging 0 in, -2 e to the 0, plus that'll be 0 over 2, minus 1/2 e to the 0. Okay. So this is -2 over e. I've got a plus 1/2. This is minus e over 2. E to the 0 is just 1. That's going to change to a plus 2. That's 0. And then this is going to change to a plus 1/2. Plugging that all into a calculator, I get approximately 0.9051. All right, let's look at another example that's a little bit more complicated in that we don't have two boundary lines that we're looking at. I've got a picture over here, so it's easier for us to see what we're going to integrate between, but if we didn't know, we would need to figure out where the intersection points of those two graphs are. We can do that by setting them equal to one another. So I will solve this, get everything onto one side and 0 on the other because it's a quadratic, so that I can factor it. X minus 2, x plus 1. All right, so I know that the place where they intersect are going to be at x equals 2 and x equals -1. I can see that on the graph, and that just helps me know where I'm going to integrate between. So the other thing that I need to do if I'm not sure from the graph is I need to pick a test point on this interval. I need to pick a test point between -1 and 2 to figure out which of the two graphs is actually the upper graph and which is the lower graph. So maybe I would pick a test point at 0. Let's test x equals 0. If I plug 0 into this one, I'm going to get 2. And if I plug 0 into this one, I'm going to get 0. So I'm just verifying that this is, in fact, the upper function and this is the lower function. So I know which one to subtract off. So we're going to take the integral from -1 to 2 of 2 minus x squared minus a negative x or 2 minus x squared plus x. All right. So this will be 2x minus x cubed over 3 plus x squared over 2 integrated between -1 and 2, or evaluated. Plugging these values in, I get 4 minus 8/3 plus 4 over 2 is 2 minus, this is a -2, that's going to change to plus 1/3 and then plus 1/2. Plug that into a calculator and I get 9/2. All right, we will do more examples like this in class. Thank you for watching.